Stanford University.
Thank you, Sally. Well, some of you have heard me speak about the future of geothermal energy before, but that was the previous future. Okay, I'm going to talk about the future. This is an updated talk based upon 2011. So I'm going to divide my talk into really three parts with a fourth part, which is by introduction. So I'm going to talk about where we are right now, where the geothermal industry has reached, and why it has reached what it has reached, and where we're going to go next in the future. So first of all, as a consequence of the last 5 years of turmoil in the oil price, the renewable energy industry as a whole has been rising at a very substantial rate. The figures I'll show you are sometimes for the world and sometimes for the United States, depending on where I could get the most colorful pictures. This is the United States, and what you see is since 2005 or so, the amount of renewable energy generated and consumed in the United States has almost doubled. Now that is all renewable energy, however that does include geothermal. Most of this, by the way, is actually wind, but this includes geothermal, wind, solar, biomass, municipal waste, etc. Hydro, for reasons that are largely political, are not generally included in the renewable energy figures, but they're shown here separately. What you will notice about hydro is that it has slowly declined over years, and that's largely a consequence sometimes of weather and sometimes a consequence of storage lakes slowly silting up. But renewable energy is substantially increasing. Renewable energy, however, is not all the same. And one of the principal advantages that geothermal energy has over other renewables is its capacity factor. Other than biofuel, geothermal energy is the kind of energy which runs all of the time, and therefore it has substantial importance in the overall portfolio of renewable energy. Not that it's the winner, but it is provides an option for baseload power which can backstop the more intermittent forms of renewable energy, by which I mean wind and solar. And what you notice here is, in fact, geothermal energy, these are actual historical figures, not projections. Geothermal energy has the highest capacity factor of any kind of energy, not just renewables, but the traditional fossil fuels as well. One of the reasons why, actually, is because a geothermal power station is very hard to start and stop. They don't like to be run in a load-following manner, and therefore they basically just run flat out all of the time. So I'd like to talk, those were the United States figures. I'd like to talk about the world figures. And every 5 years, the World Geothermal Community holds a kind of geothermal Olympics. It's the World Geothermal Congress. We had one last in 2010, and the previous one to that was 2005. And one of the things that the World Geothermal Congress does is to kind of inventory the resources of the planet, those that are in use and those that are under development. And I intentionally show you the 2005 figures because what you see here, this is where we were in 2005. The world was generating close to 9 gigawatts of electricity from geothermal at that time. And the projection was for 2010, made in 2005, that the world would produce 10,738 megawatts. Remember that number. And these are the numbers or the inventory provided in 2010. The world actually produced, at that time, 10,715. So although we actually missed by 20 megawatts, the story here, the message is that the geothermal community worldwide actually met its promise. These were not blue sky figures. These were figures that were actually met. So then you may ask, well, what is the projection of this collective community? And this is the 2010 number. This is the 2015 number. And you can see there's a substantial increase projected over the next 5 years by people who actually came through in 2010 to 18,500. And looking at the United States over the last 5 years, also this is figures from the Geothermal Energy Association. What you can see here, the green bars are the actual previous year's numbers, and the light green bars is actually what was incrementally added in terms of production capacity in each year. And what you can see is that successively every single year for the last 5 or 6 years, the United States geothermal industry has been adding capacity. So this has been a continuous development process. And at this moment, again, according to the GEA, there are 146 separate developments underway in the United States. And importantly, the different colors in here, CH stands for conventional hydrothermal. And I will talk later on about unconventional or novel methods, particularly EGS or enhanced geothermal systems. But what you see here, this is 111 projects, 111 places where they are developing conventional resources that have not been developed before. So these are greenfield developments. These ones in here are basically infills of projects that were already underway, geothermal projects that were already in use. There is a small number of enhanced geothermal systems I'll talk about a bit later on. One geopressured system, which we won't talk about today, and some co-production, which I will in fact also refer to today. These, if you like, are the sort of novel, innovative kind of projects that are coming forward currently and also into the future. And I just got this slide last week because I was in New Zealand at the New Zealand Geothermal Conference. The kind of story that I'm telling you is not unique to the United States. If you look at this rather bright green line here, this shows actually all electricity generated in New Zealand, which is 80% renewable, most of it hydro. The only non-renewable is here gas and a little bit of coal. What you can see here is that geothermal in New Zealand has increased from a historical figure here of about 8% up to 13% today, and going up to 26% in the next 5 years. So in terms of, and these are projects which are actually under development now. In terms of exponential growth, is it possible to have exponential growth in geothermal? The answer is here. Yeah. And it's yes, it is possible. So first of my 3 sort of main topics in this talk. Why are we seeing the kind of developments now in geothermal in the last 5 years that we haven't seen before? First thing I want to talk about is actual plant design. In the 30 years after which, in which geothermal first began, from 1970 or so up until the year 2000, the geothermal developments that we saw across the world were largely similar. Not completely the same, but they had very similar characteristics. That's because they were developed from very high temperature resources, basically the highest qualities that were available. And although there were differences, typically what we saw were plant sizes about 55 megawatts with turbine inlets of around 6 atmospheres, which for those of you who are mechanical engineers will recognize is actually a rather modest inlet pressure for a steam turbine, and that's because they are matched to the steam pressure and temperature of the geothermal resource itself. They're relatively inefficient compared to nuclear power plants, for example, and these kind of designs had steam consumptions between 8 and 10 kilograms of steam per kilowatt hour of generation of electricity. Starting in 2000, however, the picture changed, and there was a lot of technological advances actually applied to plant design. So in particular, there was the appearance of combined cycle plants, which is a combination of a steam flash turbine with a binary power plant. We had, or are right now having, the construction of hybrid geothermal plants hybridized with other kind of resources. And I'll show you some which are hybrids of geothermal and solar. We have examples of very high pressure inlets, again, principally governed by the resources themselves, up to 25, 26 atmospheres, with a consequence that the efficiency of the geothermal plants has increased in the last 10 years or so. Up, when I say up, this is down, because this is a consumption. You want this number to be small. 5 kilograms per kilowatt hour compared to 10 20 years ago. That's half. Twice as much electricity for the kilograms per second, yes.
Is that water vapor lost to the atmosphere or water vapor that needs to be recompressed and reinjected?
Basically, it's reinjected, although not quite all of it. Some of it is lost in the cooling tower, but 80% of it goes back in the ground.
So the more efficient it is, the better. The less makeup water you need.
Correct. And the better utilization of the resource itself. And here's an example. This is a combined cycle binary flash plant in Rotokawa in New Zealand. This is the one that has 5 kilograms per kilowatt hour consumption. And what you see here is a steam turbine in the center surrounded by binary plants. The steam comes out of the ground, passes through the flash steam plant, and the steam plant exhausts into the binary plants which surround it. Here's another picture of that. Okay, the second innovation is hybridization, combining geothermal plants with solar plants. And I'll show you 2 examples of 2 different kinds. The first is one in El Salvador where they're actually using solar collecting troughs to preheat the water and turn water into steam to increment the steam inlet to the turbine. So what you can see here is the geothermal water, which is actually a 2-phase flow, separates into steam and water. The steam goes to the turbine, and the water is usually simply re-injected. Doesn't have any useful function at all. But in that facility in El Salvador, they're using a steam generator, which is solar powered, to flash some of the separated water to steam, and it is also introduced to the same turbine. Actually, 2 different turbines, low and medium pressure. So that's a combination of geothermal with solar thermal. The second example is the combination of geothermal with solar photovoltaic. And this is a plant which is under construction now in Nevada. This picture was taken in September. So the geothermal plant is in the background. It's a binary plant, and the photovoltaic field is laid out in front of it, basically to backfill the afternoon high which they have in the Nevada power cycle. So when the sun is shining the most, 3 o'clock in the afternoon, everybody turns on their air conditioners, and the photovoltaics add 23 megawatts to the 47 megawatts that is being supplied basically all of the time with geothermal energy. For those of you, again, who are mechanical engineers will recognize the symbiotic nature of those 2 functions. The binary power plant in the background has air-cooled condensers to recondense the fluids. Those air-cooled condensers are least efficient when the air temperature is high, which is 3 o'clock in the afternoon. So the geothermal power plant runs best at night and worst at 3 o'clock in the afternoon. The photovoltaics are exactly the opposite. They don't work at all at night, and they work best at 3 o'clock in the afternoon when the sun is shining. So you put the 2 together, they basically backfill the shallow valleys in each of their production characteristics. Yes?
Related to my earlier question, would this plant then effectively have 0 net water consumption?
Correct. The binary plant has no water loss at all because all of the fluid goes into the ground. Okay, the third thing about the changes that have happened in recent times is that we, by, again, innovation in plant design, are moving downwards in temperature of the resources that we exploit. The kind of flash steam plant I showed you of the historical kind, 55 megawatts, etc., the ones that have been used in the past, were typically using resource temperatures 220 degrees and up as high as 300 degrees centigrade. And those kind of high-quality resources, although there's quite many of them in the world, are largely exploited already. There are some left. Some of those I showed you in New Zealand, and there's quite a few in Indonesia as well. But most of the good ones have been exploited already. So there weren't very many of those. There are many more moderate to low temperature resources. They exist pervasively actually across the planet. And here is an example in the state of Alaska in a very nice place called Chena Hot Springs. I recommend you go there if you ever have the chance. It's a resort about 90 miles from Fairbanks, the city of Fairbanks. And in fact, the power line ends just at the outskirts of the city of Fairbanks. And China previously, or even now in fact, is 90 miles from the closest power grid. And up until about 5 or 6 years ago, they generated their electric capacity for the resort, which is quite a large resort, has 200-300 beds. People go there for the hot springs and watch the aurora and all that kind of stuff. They had to generate their own electricity, and they will probably never be on the grid, at least not for another 20 years or so. So they built this geothermal plant to capitalize on the thermal energy of the hot springs in the resort, and importantly, they are recovering, or they're generating electricity from a water temperature of 74 degrees centigrade, which is actually a world record in terms of minimum value. And to give yourself a reference, a hot tub, if you're really keen on hot tubs and like it really hot, the temperature in a very hot tub is about 45 degrees centigrade. So this is somewhat, but not hugely hotter than that. Depending on your personal preference, hot water in a house is often set around 60 degrees that you do your washing in and things like that, 60 degrees centigrade. And this unit is also kind of innovative. It's basically an industrial air conditioning unit running in reverse. So instead of actually consuming electricity and providing coolth, it's absorbing heat and providing electricity. It's an air conditioner run backwards with very small modification made by UTC. Okay, and that kind of resource opens up a lot of possibilities. Like China hot springs, there are a lot of isolated communities that are not provided with grid power. A fine example is small islands. A lot of the islands in the Aleutian chain, islands of the Caribbean, islands anywhere basically, isolated grids have no way of transmitting electricity from larger generating capacity units, and therefore they often use diesel generators, which is very expensive, very inefficient, and also produces a lot of carbon. A second example is the capturing of electricity from places that have excess hot water. And a rather classic example for political reasons is the hot spring spas called onsens in Japan. And the reason I mention them specifically is that one of the holdups for geothermal development in the nation of Japan is that the hot spring owners hate the whole idea. They don't want geothermal development because they're afraid they're going to lose their hot water supply into their hot springs, which is how they make their living in the hotels. It turns out, however, that in many of the resources that supply the hot springs in the hotels, the temperature is too high. They're providing temperatures, 70 to 80 degrees. That's too hot to bathe in, and therefore they have spray towers that spray the water up in the air to cool it down before it goes into the baths. And someone pointed out that instead of just cooling the water in spray towers, they could run it through a turbine or a small binary unit or whatever, supply the electricity for the hotel, which they're gigantic hotels in many cases, and then still have the hot water they need for the spa. So that's become a very popular idea in Japan, especially in the last 12 months. And then finally, I'm going to talk about co-produced fluids, which is the production of fluids for other purposes, typically for oilfield operations. I'll talk about that in a moment. So here are some examples. This is a geothermal development taking place in the Aleutian island of Akutan in Alaska. It's a small island, has a population of about 50 people only, but it also has a very large industrial electrical requirement because they have a large fish canning factory that actually requires about 11 megawatts of electricity when it's in operation because they're cooking fish and making canning machines, etc., during the summer. So instead of using diesel at a cost of 60 cents per kilowatt hour, they are making use or going forward with making use of the geothermal resource that exists actually on very many of the Aleutian Island chain. They're basically a volcanic belt which runs all the way down the chain, including on this island, Unalaska, Dutch Harbor, All of those islands have geothermal resources. Okay, so let me talk about co-produced fluids. The worldwide oil industry currently produces about 85 million barrels of oil per day, and also about 300 million barrels a day of water. So because of the high water fraction, companies like Exxon and Chevron are actually more water companies than they are oil companies. They produce 4 times as much water as they produce oil. And a lot of that water is quite hot. Not all, but a decent amount. So here's an example. In Wyoming, this is the Rocky Mountain Oilfield Testing Center, which belongs to DOE. It's constructed on the infamous Teapot Dome oil field, which was for a long time the Naval Oil Reserve. And it happens that that particular field produces water, you see here, at around 92 degrees centigrade. And up until recently, that water, because it's relatively fresh, was basically just tossed in the river. However, before throwing in the river, because it's 92 degrees centigrade, they actually passed it through a cooling tower to dissipate the heat before they threw it away. So they replaced the cooling tower with this binary geothermal power plant, and they are now generating 216 kilowatts, which provides actually some fraction of the electricity for the oil field operation itself. You know, this and many oil fields actually are large consumers of electricity running the pumping units, and this provides about half of the electrical capacity or requirement for the field. Currently, they are in the process of installing a second one of these because they weren't using all of the water. They were only using this amount of it, 25,000 barrels a day, and they will soon be generating a second 300 kilowatt supply in Teapot Dome. This is a second example. This is in Huabei oil field in China. They have 2 separate reservoirs with 2 different temperatures, 110 and 120 degrees, and they installed this binary power plant, which is currently producing 400 kilowatts of electricity. Okay, and one of our students in the Energy Resources Engineering Department, Kara Bennett, actually did a study of the electrical geothermal capacity from co-produced fluids in the Los Angeles Basin. This is Long Beach Harbor. And although a lot of people don't fully recognize this, the Los Angeles Basin is underlain by a significant number of rather large oil fields. This is the biggest one here, Wilmington Oil Field, which is a genuine supergiant. It was discovered, however, a very long time ago in the early 1900s and is largely played out. It doesn't produce a huge amount of oil anymore, although a decent amount. What it does produce, nonetheless, is a very significant amount of water. So you can see here of the LA Basin, the average water production is 97%. For every 3 barrels of oil they produce 97 barrels of water, much of it quite hot. So in total, there are 49 separate oil fields, and because they have production intervals at different elevations, there are a total of 365 independent oil reservoirs in the LA Basin. The geothermal gradient is basically normal. The worldwide average is 30 degrees centigrade per kilometer. That's quite distinct from what we see in the high temperature resources in Indonesia, New Zealand, etc., which are more like 200 degrees centigrade per kilometer. So there are tens of thousands of wells in the LA Basin. These are not wells. Each one of these is actually just a reservoir, not a well. And you can see that some of them are rather deep. They are up to 3.5 kilometers deep, and they're also rather hot, 140 to 160 degrees centigrade. So those are certainly geothermally interesting temperatures for the generation of electricity. And these 4 colored dots actually pick out 4 particular reservoirs that happen to be of interest. So this is all 49 oil fields, but just the names are cut off because you can just see the interesting ones. There are 6 in here in particular that Kara picked out as those which have a power potential that gives them a net present value in excess of $1 million. So if we see them in the table here, the biggest one is Wilmington oil field. It has a potential power capacity of 3.5 megawatts, and in total, they add them all together, 7.5 megawatts, and a net present value of $41 million. Now let me point out what an attractive idea co-produced fluids are. This is not drilling wells and producing fluids and putting them into a power plant. This is basically free money. All this requires is a T in a pipe. You separate the water and pass it through the binary power plant, producing the water which is already in your hands. And after it passes through the binary power plant, it goes back into the pipeline again and goes back in the ground the way that it does today. This net present value includes the cost of the power plant itself as well as its operation. So this could supply a significant fraction of the electricity that's actually being used by those oil production facilities today. Okay, and oil field operations are not the only kind of co-produced fluids that we can talk about. And this is another example. This is a heating scheme in Germany where they're producing water at 99 degrees centigrade, just short of boiling. Remember some of these numbers, by the way, the kilograms per second. It'll be important a bit later on. They're producing 30 kilograms per second into this binary power plant, and they're producing 210 kilowatts of electricity, together with the thermal energy that they circulate through the space heating in the buildings of the town. So you can see here the representation of the subsurface. They're pumping the water out of the subsurface through heat exchangers. Here's the electrical plant, and then after the electrical plant, it goes into the space heating, and ultimately the cooled water goes back into the ground again. And there's a number of this kind of facilities throughout continental Europe, outside of the volcanic regions. So Germany has many resources like this. They are relatively high temperature, closer than expected to the surface, because of the rather advantageous insulating the conductivities of the formations that are in the shallower subsurface. They have a lot of coal in Germany, which is generally an insulator. They have quite decent temperatures at attainable depths. The same is true, rather surprisingly, of the Paris basin. And the city of Paris has more than 80 geothermal heating schemes where they take water out of the ground like this, pass it through the buildings, and put it back again into the ground. Okay, now I'd like to make an observation here. It's this sort of a technical point that hotter isn't always better. I showed you examples from 74 to 160 degrees, but there is a kind of a gap in the technology. If we have these low temperature resources that I've been showing you, the wells need to be pumped. They have either a shaft-driven pump or sometimes an electrical submersible pump, which lifts the fluid to the surface so it circulates through the binary plant. That's typically the way they operate. The conventional hydrothermal resources that we saw earlier, the wells self-flow by flashing to steam in the wellbore. They're basically like coffee percolators. They boil and lift the hot water to the surface. A flashed well or self-flowing well doesn't really get a decent sort of flow until it's over here above 220 degrees centigrade. That's the reason for those being the traditional kind of resources that I showed earlier. The more modern ones, or the more recently attained ones, use pumped wells, and pumped wells are really not attainable at temperatures above 190 degrees centigrade. And the reason for that is that it's difficult to have a mechanical device working at that temperature year in and year out. You've got maybe slightly saline fluids, which may be corrosive. You've got high temperatures working on the seals, the electrical connections, and things like that. And although they have pumps that run at 200 degrees centigrade, they don't run necessarily with huge reliability. If you have to pull the pump out every 6 months, it's going to cost a lot of money, and that goes into the operating cost of the plant. So currently there's a gap between about 190 degrees and 220 degrees where the resources are too cool to be self-flowing and too hot to be pumped. And that represents actually quite a large fraction of the resources of the planet. And this is a technological advance which needs to be made if we're going to actually fill that gap. What we need, basically, we can't do anything about the flashed wells. What we can do is to improve the pump technology so that we can pump water up to 220 degrees centigrade reliably. All right, so let me move on to my fourth and final topic, which is enhanced geothermal systems. The kind of resources I've shown you so far rely on water passing through the subsurface so it can be brought to the surface and its energy extracted. There are lots of places, however, in the world where, although the subsurface is hot, the rock is not permeable enough for the fluids to pass through. And that means that the kilojoules are locked into the ground and we can't get them out. And the idea in an enhanced geothermal system is to create your own permeability. And that's done by fracturing the rock, either with typically with hydraulic means, although that's not the only way. So you drill a series of wells, you fracture the rock, and pass the fluid through those created fractures to recover the heat. It's an in-place heat exchanger, if you like. So it depends on fracturing. It's a technology which is sort of discussed quite a lot. I'll come back to it in a second. If you look at the United States, this is a map of the temperature of the United States at 6 kilometers depth, which is what we can attain with current drilling technology. And you can see the temperature range here. Remember, binary power plants are attainable or currently applied in the range of 140 to 150 degrees, this kind of red color. And most of the western United States and quite a lot of the Gulf Coast actually has those kinds of temperatures at the drillable depth. So all of this, if you like, would be an attainable target for enhanced geothermal systems if they were to be made routinely workable. However, it's important to recognize that there are some issues that we need to solve before we can apply EGS with that kind of routine facility. Getting these things to work requires a number of things. First of all, because they depend on conduction rather than their own sort of native permeability, what we need to achieve is a high surface to volume ratio. Conduction doesn't carry the heat very effectively through the volumes of rock. Therefore, we have to fracture the rock a lot in order to be able to attain a reasonable amount of heat. We also have to place those fractures in a way which is advantageous to keeping that heat continuously operating. If you have just one big fracture and you pass cold water through it, after a couple of months or so, you get a thermal breakthrough, you cool down the rock close to the fracture, and then the project is over. And there may be plenty of heat left, but it's no longer accessible to you. You have to have a network of fractures. You have to be able to control it, and you have to be able to monitor it to get the most of what there is to be had. We have to have sufficient flow rates. And again, I asked you to pay attention to the numbers there. The figures that are being talked about for EGS systems are of order 80 kilograms per second. And to convert that into oil field terms, that is 50,000 barrels a day. That's a lot of fluid to ask a well to be producing. And finally, we have not perhaps a technical issue, but a public relations one, which is induced seismicity. The fracturing process and the production of the resources themselves tends to produce microseismicity. And although most of the events are of order 1 or 2, there have been several examples where EGS systems have produced seismic events up to magnitude 4. And people don't like that if they're not accustomed to earthquakes. You know, around here, 4 is kind of small potatoes. But if you're in Basel, Switzerland, where they had a 3.4 earthquake, that upset a lot of people, and it actually caused the EGS project there to be shut down. Okay, so let's come back to this 80 kilograms per second. There was a very famous paper called the MIT report, actually a big thick one, in 2007, that was largely responsible for a great deal of the enthusiasm currently being shown towards EGS in the United States and in other countries as well. And this is their calculation of what electricity price could be achieved as we grew through the learning curve of developing EGS projects. And you can see here they're coming down here to 4 cents per kilowatt hour. That, of course, is a magic number because that's what, at least in 2007, was competitive with natural gas, which is gas and coal are the two cheapest electricities we generate. But this whole calculation was premised on 80 kilograms per second per well, which I mentioned before. Now, 80 kilograms per second, 50,000 barrels a day, is a huge amount for an oil well. However, it's not such a big amount for a geothermal well. And I just picked one out of my files here. This is a conventional geothermal well from the kind of resources that we've been producing for the last 50 years. The red line is the total production, blue is water and black is steam. You can see it. And this particular well is producing about 70 kilograms per second. So certainly attainable. That's done every day. However, the EGS systems that have been developed experimentally up till this time have not done so well. And this is an example of one of the most modern ones, which is in Soultz in eastern France, just close to the border with Germany. And you can see here, these are their numbers. In this particular test, they were producing about 10 kilograms per second. This is another one in Japan, again, an experimental EGS system done with sort of government support. They're producing here about 8 kilograms per second, this pink line right here. Let me skip that one. Here's a third one, which is in Cooper Basin in Australia. Rather remarkably, Australia has a quite vigorous geothermal industry in spite of having not a single active volcano in their country. So they are completely focused on EGS. Well, not completely. They're also doing some of these deep sedimentary aquifers like I showed you in Teapot Dome. So in this particular study, or this particular test in 2005, they were producing 20 kilograms per second. Notice the temperature here, 210 degrees from a well at 4 kilometers depth, right in the middle of Australia. And Doon Wyborn, who is one of the workers in that project in Australia, made this summary of basically all of the research EGS systems that have been installed in the world. And I added this red bar here to draw your attention to the most successful ones. Cooper Basin, that's the one I just showed you a second ago, subsequently produced as much as 30 kilograms per second. Here is Soultz, the one I showed you before. The maximum it ever produced was 25 kilograms per second. So you can say, well, you know, so far we've not been doing very well if 80 kilograms per second is what we're asking for on a routine basis. However, there is one that actually did that. There's one here in Landau, Germany. It's this place right here, where they did in fact produce 80 kilograms per second. They actually are capable of producing as much as 100, but in routine operation they're producing here 70. So they have this binary power plant there, it's produced 3 megawatts of electricity. And rather fortunately, because of the geology of that part of Germany, they achieved this temperature, 175 degrees, at only 2.5 kilometers depth, which is a very advantageous thing because it's a whole lot cheaper to drill to 2.5 kilometers than it is to drill to 4. And this plant is in commercial operation and has been since 2008. It's basically the first commercial enhanced geothermal system operating in the world today. So can we do this routinely? We don't actually know this. However, as a geothermal community, we've done it once, okay? And therefore there is in fact at least the opening of a possibility that we can do it again. Let me pass over that one. So one of the things I'd like to draw your attention to when we sort of take this in context, I'm drawing a comparison here between the 3 different kinds of resources that I've shown you. The one at the top, this is Soultz, the 3 different kinds. EGS, this is conventional at the bottom, and in the middle we have the sedimentary basins. like the one I showed you in the middle. Groß-Schönebrück is in Germany. And the number to look at here is not so much the kilograms per second, which is how much you just happen to produce, but your productivity, how much you could produce based upon the pressure drop that you supply with your pumps. And looking at the conventional system first, that was the first one I showed you, producing 70 kilograms per second. This kind of typical of a conventional volcanic geothermal system has a productivity of around 11 kilograms per second per bar drawdown of pressure. The sedimentary basins are about half that, 4 to 5, and the EGS system in salts is about 1/10 of that. The difficulty is, as I mentioned to you earlier, to get that productivity to create enough fracture permeability that you can pass enough fluid through the system. And that is currently where the hang-up lies, or one of the hang-ups with EGS. Don't think, however, that my remarks suggest any kind of concern, if you like, that this kind of technology can't move forward. And this is because this is a list of EGS projects that are currently under development in the United States, and there are 6 of them. So these are, for the most part, commercial entities who are attempting to develop EGS systems in the United States. This last one here is kind of interesting in that this company is producing an EGS system that is going to use CO2 as its working fluid rather than water. And the reason that's advantageous is that many of the EGS systems that I showed you, the research ones, have lost water because the permeability isn't all connected. You put water in it, you don't get it all back again. In a state like Nevada, that's a significant problem because they don't have much water. And if you had to make it up, it would be a difficulty. If you put CO2 in as the circulating fluid and you lose some, you're doubly happy, okay? Getting rid of CO2 is what the whole process is about. So circulating CO2 in your working fluid has a double advantage. It also happens to have advantages in terms of its thermal conductivity as well. So let me draw this to a close. In the last 5-6 years, there has been a significant series of changes in the geothermal development of the resources worldwide. And it's happened in that period specifically, largely as a function of the cost of hydrocarbon resources during that time. There's a lot of new companies and new countries who have joined the playing field, if you like. And these include, importantly, a lot of countries that are not traditional geothermal countries. You know, the hot places in the world, the Pacific Ring of Fire, which includes all of the significant volcanic resources of the planet, countries like the United States, Chile, New Zealand, Philippines, Indonesia, Japan, all of those are very hot places, very active volcanically, and filled with geothermal resources. Italy is another one. Iceland is a third example. But these countries that have got into the act more recently, since 2005, include those ones I mentioned that have no history of volcanic activity at all. Germany, Switzerland, Sweden, and France, and Australia, places that you wouldn't previously have associated with geothermal activity. A lot of new technologies that I've shown to you, power plant design, hybridization, etc. The attainability of lower resource temperatures, which makes possible geothermal developments in a lot of places where it formerly was not. And finally, although we haven't achieved it routinely, we do in fact have promise of EGS to supply geothermal energy in places where we previously couldn't have imagined it. And finally, I will observe that the sun does not set on geothermal energy. So thank you very much.
Okay, questions? How about right back there?
In the opening, you mentioned the trend of an improvement of about 8 to 10 kilograms of steam per kilowatt hour, improving to about 5. and at the same time we're using lower temperature resource, which I would have thought you have lower energy per unit and you have less efficiency because of Carnot. How much of that is driven by the temperature hole you mentioned, and how much are other things?
Yeah, so you're quite right. They go in opposite directions. So as you go to lower temperatures, the efficiency actually gets worse. And the example I showed you going from 10 to 5 were basically the same kind of resources that were used before. So 220 to 250 degrees centigrade resources, they've been able to go from 10 to 5. The lower temperature resources don't achieve anything like that. However, they are also more efficient than they were 10, 20 years ago because of the design of the binary plants. But they're not achieving, well, it's hard to compare because binary plants don't consume steam at all. But their thermal efficiencies are not as high as those flash plants.
Yeah, about back there.
Regarding the co-produced fluids and oil reservoirs, have you investigated the potential impact of oil production as you extract heat from the reservoir and as it cools down?
No, although we're in the process of doing that right now. The principal concern is that if you lower the temperature of the reservoir, you make the oil more viscous and therefore it's harder to flow. However, if you bear in mind that you're producing 97% water, actually I would suspect that that's not a very large effect, although we actually don't know that. Another kind of resource which we happen to have a lot of in California is previously steam-flooded reservoirs, in which steam is injected into the ground specifically to lower the viscosity of the oil. I say a lot. Some of those resources are now in the process of being abandoned. There's a lot of kilojoules down there in the ground which was put there over the last 50 years in the steam flooding operation, which could be recovered this way. Whether or not there's any oil comes with it at all, the wells can be kept in operation. They've already been paid for. The pumps are already there. You could, in fact, recover some of that heat that was previously just placed into the ground.
Okay. Yeah.
So Roland, in that St. John's Dome CO2 circulating experiment, where does the CO2 come from?
I actually don't know where they're going to get it from, but they're either going to take it from a separation, a capture plant, or maybe they're just going to take it from a CO2 reservoir.
Yeah, because it seems to me if you have to buy the CO2, then losing it has a negative.
It's not such a good idea. You're right. It's a demonstration project, but ultimately what you would imagine is you have a coal-fired plant, you capture the CO2, and you have an EGS CO2 system running next to it.
Okay. All right, we'll go here and then we'll go over there.
Are the exploration risks and costs comparable to the oil and gas industry?
They are actually higher. Geothermal tends to be expensive for a number of reasons that, number one, the biggest additional cost in geothermal over oil and gas is drilling, because you're typically drilling in hard rock instead of drilling in soft rock. So drilling geothermal wells is much more expensive. The exploration costs are also often higher because it's hard to actually describe. We actually have better ways of finding geothermal reservoirs than we do have oil and gas, because the high temperatures are actually sort of measurable from the surface. We can measure the temperature gradients, we can measure the electric resistivity, because the hot fluids are more conductive. The problem is, however, that you've got to find much larger volumes of reservoir in order to produce commercial quantities of geothermal heat. So it's easier to find them, but it's harder to find big ones.
We'll go over here and then over there.
Roland, the cooling tower applications where the heat doesn't come from inside the earth that this technology opens up, air conditioning systems, or the waste steam from power plants, coal-fired power plants, nuclear power plants, other places where there's a tremendous amount of waste heat.
Yes, there are many. So waste heat recovery is sort of a whole, it wouldn't be correct to call that geothermal, but the same technology is actually applicable and applied in several, in many different operations. The power plants that are commonly used in geothermal fields are most often supplied by a company in Nevada called Ormat, and they've made that their sort of niche in the industry. But Ormat also supplies heat recovery units for gas turbines. And they supply them across. A lot of the natural gas pipelines in the United States have compressors that are gas turbine driven that consume some of the gas in the pipeline to pump it up to send it along the rest of the way. They're actually, and typically they have 2 turbines. So if one breaks, they've got another one available. What they're able to do is to actually take the heat from the turbine exhaust of one turbine and replace the next turbine down the line, basically. So they're halving their consumption by recovering the heat from some of the turbines.
All right, how about there?
There were some demonstration projects where the heat was recovered from either in the ocean, sea, or in Israel from ponds, either from geothermal or heated by sun. How are those projects fit into your geothermal, or how you compare? What is the status, if you can comment, please?
Well, I actually don't know the real answer to that, but Ormat, the company I just mentioned, is based in Israel. They have a headquarters in Nevada, but their original concept was solar ponds. So you have a very saline water like the Dead Sea, but you make your own. And because of the sun shining on the pond, you have a gradation of temperature between the top and the bottom. And the plants that they built were originally built to capture that heat contrast between the top and the bottom of the pond. But they found, first of all, that it uses a lot of land and a lot of water to make that. And secondly, it doesn't make a lot of electricity, and they transferred the technology to geothermal. But that was the original idea.
Okay, one back there.
What is the commercial potential in terms of megawatts or gigawatts of opportunity, and at what price per kilowatt hour steps?
It's a good question. So the MIT report in 2007 talked a lot about EGS, and they made an inventory. Like the map I showed you came from that report. And their figure was 100,000 megawatts nationwide. And that happens to be a significant figure in that right now the electric capacity of the United States is about 1 terawatt, 1,000 gigawatts? Yeah, 1,000 gigawatts. So 100,000 gigawatts is 1/10 of that. But they were projecting 100,000 gigawatts in the year 2050, by which time the national capacity is expected to be 2 terawatts. So it's 5%. And the reason why 5% is important is because right now, the state of California generates 5% of its electricity from geothermal resources. So the reason that 5% was sort of a magic number is because the premise of the MIT report is that the nation could achieve what California currently achieves with geothermal generation. And I showed you the graph during the talk. They were projecting 4 cents per kilowatt hour at a time when market penetration reached 10,000 megawatts.
Okay, we'll take one more question and then we'll wrap up. How about back there? Yeah, you go.
Recently in the news, there's been a couple articles about geothermal plants as it relates to the government guarantee. There's one in Utah and one in Nevada that have had financial problems. Can you comment on why those companies or projects have had financial problems?
Sure, there was a famous one in Utah that it's the Cylindra alternative, if you like, alter ego, that's named after a Republican senator who supported it through Congress. And there was a substantial amount of stimulus money, $400 million actually put into geothermal energy in 2009 that was used for loan guarantees, and the 6 projects I showed you, 5 of them have stimulus money into them to encourage them. They're not 100% supported that way, but 20%, something like that. You know, there was a lot of how can I say it, speed that was required for people to capitalize on those funds. In other words, they had to generate, or they had to construct and develop projects in a much shorter period of time than is often used for geothermal because of the drilling, etc., construction time. It's typically 4 or 5 years to put a geothermal plant into operation. Some of those ones, including the one in Utah, were actually constructed in 18 months to 2 years, very, very quickly. And what actually ultimately happened is that they built a power plant. Don't quote me on this. This is my speculation. They probably built a power plant that was too big for the steam supply, and therefore they couldn't keep it in full operation. It's perfect. I mean, it's an operating plant, nothing wrong with it, but the resource doesn't have sufficient steam to put it into full operation, so it's losing money.
All right, well, I think it's time to wrap up, so thank you very much.
Thank you.
For more, please visit us at stanford.edu.